about calculations using the combined gas law. The combined gas law combines Boyle's, Charles, and the Gay-Lussac or pressure-temperature relationship into one convenient law that we're able to use. One thing that we have to kind of keep in mind with this is we are talking about a fixed sample of gas with a certain number of moles. We don't need to know what that number of moles is. We just know that the amount is not changing. So this is a container that is not allowing particles in or out of it. So if we put these laws together, because Boyle relates pressure and volume, then Charles relates volume and temperature, we can relate, because of that, we can relate pressure and volume and temperature, and then we're able to also use Gay-Lussac's to tie the whole thing together. So we can put these three laws together, and we get a law that you'll find in the back of your reference table. P1 V1 over T1 equals P2 V2 over T2. What this means is that if you have an initial set of conditions and a final set of conditions for a sample of a gas with a fixed number of moles, you can multiply these things and they will come out equal. What's nice about this law is it also allows us to cross out something that is constant if we need to. So we'll talk about what that means in a minute. So when using the combined gas law, a couple of things to keep in mind. You must convert all Kelvin temperature or all Celsius temperatures to Kelvin. Everything has to be in Kelvin. And if you have any constants, you need to cross them out as well. Two special notes again. Remember, your temperatures are going to be in Kelvin, and your number of moles is going to be fixed. You don't need to know what that number of moles is. You just know that it is not changing. So just keep that in mind. So we're starting with a sample of gas with a volume of 4 liters and a pressure of 205 kPa. We're going to allow that gas to expand to a volume of 12 liters. What is the pressure in the container? The temperature remains constant. So we're going to write what we know first. We have an initial volume of 4.00 liters. We have an initial pressure of 205 kPa. We're going to get a second volume of 12 liters. The pressure, our second pressure, we don't know. That's what we're going to be solving for, and that is going to come out in kPa. We also know something about temperature. We know temperature 1 is equal to temperature 2. This is important. I want to just pull you aside for a minute and talk about what that actually means. So in this law, so P1, if T1 and T2 are equal to each other, so we can actually just take out the 1 and the 2, means we have a T on each side in the exact same place. So imagine that each one of those with a number 5, for example. If you had a 5 here and a 5 here in this equation, because they're in the same place on opposite sides of the equation, you would cancel them out. So what that allows us to do is cancel out our constants in this equation, which is really nice. So since if something is constant, you basically get to kind of ignore it. Step 2 we don't have to worry about here. We don't have any temperatures that we're dealing with. What we are solving for, we mentioned above, is P2, which is in kilopascals. We're going to write our equation. P1 V1 over T1 equals P2 V2 over T2. As discussed above, T2 will go away. So now we can just plug in our P1, it's 205 kPa. Our V1 is 4 liters. Our P2 is our X, we don't know that. And our V2 is 12 liters. So you're going to go ahead and solve. You're multiplying 205 by 4 and divide that by 12. It should give you 68.3 kilopascals. I'm using 3 sig figs here because each of these numbers had 3 sig figs in them. So please take a minute. In this one, it's a little bit more difficult. You actually have to plug in all three things. Take a minute, try this problem and the next one, pause the video. I do want to do the last problem together. So try the next two problems, pause the video. Keep in mind, you may have to convert between Kelvin and Celsius. So the answer you should have gotten for this problem is 0.342 liters. To walk through this with you and show you your work, we have a P1 of 155 kPa, a T1 of 298 K, and we also have an initial volume of 1 liter. Pressure of the gas is going to change to 605 kPa, and our temperature changes to 398 K. Our new volume is what we don't know, and that will come out in liters since our other volume is in liters. Yes, our temperatures are in Kelvin. We are solving for V2, and again, double check your liters. We know it will be in liters because our other volume is in liters. So we're going to use our whole P1, V1 over T1 equals P2, V2 over T2. Now when we are plugging into this equation, if you did not get this answer right, it is probably something involving how you did your algebra. So be very attentive to how I'm plugging in. We have 155 kPa times 1 liter over 298 K. 605 kPa times our V2 or our X over 398 K. Mathematically, what is happening here is you are cross-multiplying this, okay, and you are cross-multiplying this. So to do this really cautiously and stepwise, if you're not very comfortable with algebra, is a great idea. You would get, for this one right here, you're going to get 61690 equals 180290 times V2 or X. Got to divide both sides by that. And that will go away. So that's what's going to give you your 0.342 liters. So be very cautious. If you have three variables, it's pretty easy to screw up the math. So be very cautious with that. The answer to the other problem, hopefully you converted to Kelvin to get 8.36 liters. So I'll walk through this for you. Your knowns, we have a V1 of 5 liter, T1 of negative 50 Celsius. We have a V2 of 100 Celsius and a P2, oops, sorry, that is not a V2. We have a V2 of we don't know, and we have a T2 of 100 degrees Celsius. P1 is equal to P2, so our pressures are constant here. Step 2 reminds us that no, we are going to have to convert. So you're adding 273. Remember, that's a negative 50, so this is actually going to give you 223K. And then 100 plus 273 gives you 373K for your second temperature. We are solving for V2. V2 will come out in liters. In our equation, we are going to be able to cancel out our pressure. So this is just going to be V1 over T1 equals V2 over T2. When I plug in, I'm putting 5 liters over 223 Kelvin, and I'm putting V2 over 373 Kelvin. So once you cross multiply that and divide out, you should get 8.36. Last problem I wanted to talk about together because it has STP in it. So we have a 1.5 liter sample of gas being held at STP. It doesn't look like numbers, numbers, but it represents numbers. The temperature is going to be changed to 300 K while the pressure is held constant. What is the volume of the gas? What volume does the gas now occupy? So my initial volume is 1.5 liter. My second condition that they have given me, they're telling me I don't know my second volume, and they're telling me that I have a second temperature of 300 K. They're also telling me P1 equals P2, so my pressure is constant. So you might say to yourself, I'm missing a piece of information here. What the heck is my T1? That's where the STP comes into play. STP means go to table A. There is a temperature on there for you. And that temperature, standard temperature, is 273 Kelvin. So you'll just choose the Kelvin one there. Are all of my temperatures in Kelvin? Yes, they are. I am solving for V2. That will come out in liters. I'm able to cancel out pressure here, so this is going to be volume 1 over temperature 1 equals volume 2 over temperature 2. When I'm plugging in, I'm going to have a 1.5 liter sample at my 273 Kelvin equal to my V2 over my 373 Kelvin. So when you cross out, or when you cross multiply and divide out as needed, you should get 1.7 liters, and I am limited to 2 sig figs here.